Okay, so we're going to look at how we are supposed to write Lewis structures for our molecules at this point. We use Lewis structures to write, to draw the structures out between covalently bonded molecules, not so much for ionic. For ionic bonding, we do that thing that we noted at the beginning of the chapter 9 videos where we write the ions next to one another. But when we have covalent bonds, we actually need to draw those bonds out, and we need to draw the lone pairs out that surround our atoms. So we have a procedure for doing this, okay? We're going to start by first looking at all of the atoms that make up our structure, and we're going to calculate the total number of valence electrons that are available for our structure. Okay, we're going to note that number on the side. We can circle it or something, and we'll keep that handy. Next, we're going to write out the correct skeletal structure for our molecule. Okay, a skeleton structure means that you'll connect everything by only one bond initially. We're going to put the least electronegative atom in the center position. Hydrogen atoms are always going to be terminal atoms. Hydrogen can never be our central atom. And the more electronegative atoms, things like chlorine or fluorine, those are going to be placed in terminal positions unless they're in a compound with something else that's more electronegative than they are. After we're done writing our skeleton structure, then we'll distribute the electrons left among all of the atoms, and we're going to give octets to everything possible. Okay, everything wants an octet except for hydrogen, which only wants 2 electrons. If any atom lacks an octet, we can form double bonds, we can form triple bonds, we could do whatever we need to do to make sure that everything gets an octet in the end. And at the end of drawing our structure, we need to count up the electrons that we used, and we need to make sure it matches the number of electrons that we initially counted. Then we have to make sure that everything has an octet again. Okay? It gets overlooked, surprisingly, and we can't overlook it. So we're going to go through these examples. All right? I'd recommend at this point, per usual, that you pause this and you try to do the Lewis structures out for these four compounds, and then we can work through them together. All right? Okay, let's start with NH3. So thinking back to step 1 of our to-do list, we need to calculate the total number of electrons available for the Lewis structures by summing up the valence electrons present. So what I like to do is underneath each of my atoms, or on top, we can do it on top here, I like to write out the number of valence electrons that each thing has. So every nitrogen has 5 valence electrons. I know that because nitrogen's in group 5. Every hydrogen has 1 valence electron. It's in group 1. So now I'm going to figure out how many valence electrons that I have available by adding them all together. So 5 plus 3 times 1, because I've got 3 hydrogens. So I have 8 valence electrons available for this structure. So now my next step is I'm going to write out my skeleton structure. So obviously hydrogen can't be a central atom. It's only a terminal atom, so nitrogen has to be in the middle. So I'm going to draw a skeleton structure with nitrogen in the middle and my 3 hydrogens surrounding it. Okay. And I'm going to complete the octet of anything that needs its octet completed, which means nitrogen needs a pair of electrons there. So now I'm going to do some counting and see where I'm at with my structure. First of all, how many electrons did I use? I used 2 for this bond, 2 for this bond, and 2 for this bond. So that's 6. Plus my 2 up here is my lone pair. That's 8. that matches my valence number, which is good. That means that I've done well there. Now I have to check to see that everything has an octet or a duet. Each of my hydrogens has a duet because it's bound to my nitrogen. So I have 2 electrons there for that one, 2 for this one, 2 for this one. My nitrogen has 2, 4, 6, 7, 8 around it. It's happy. So this is a good structure. Okay, our next structure is CO. Okay, so carbon has 4 valence electrons. Oxygen has 6 valence electrons. That means that there are 10 valence electrons total. Oops, valence electrons. So that's what we have available. So my second step now will be to write out my skeleton structure. In this case, I only have 2 atoms, so there is no central. I just have a sort of line right there. Right? Now I'm going to put electrons around both of my atoms, and I'm going to give them an octet. And I want to see how many electrons that costs. So if everything has an octet, that costs me 2, 4, 6, 8, 10, 12. That costs me 14 electrons. Unfortunately, I only have 10 electrons. That means that I have a deficit right now, right? I have a 4 electron deficit. Well, I can make up that electron deficit by adding multiple bonds into my structure, okay? Every bond equals 2 electrons, okay? So I'm missing 4 electrons for this structure. That means that I'm going to need to add 2 bonds to it, right? Now, the thing is that every time that I add a bond to this structure, I get to remove 4 electrons from my skeleton here, okay? Because now instead of each atom having its own lone pair of electrons, now they're going to share a set of electrons instead, okay? So I know that I'm missing 2 bonds. So I'm going to remove these 2 electrons. I'm going to put a bond between them. And if we're keeping track now, we see that I had 14, and now I have 2, 4, 6, 8, 10, 12. Okay, well, let me do that again. Let me remove these electrons and add a bond here. Now I have 2, 4, 6, 8, 10 electrons total, which is my valence number. And my carbon has 8 electrons around it, and my oxygen has 8 electrons around it. So that is a good structure. H2CO. Okay, so my total valence here, put a little 2 times in front of there. So my total here is 12 valence electrons. Okay, carbon is my least electronegative, so it will be in the center. I'm going to surround it with everything else. Okay, and now I'm going to fill the octets of my carbon and my oxygen. So right now my carbon has 2, 4, 6 electrons around it. So I'll add a pair there. Oxygen only has 2. So I'm going to add enough electrons for it to have an octet. And now I'm going to do my counting. So I've got 2, 4, 6, 8, 10, 12, 14 electrons here. I only have 12 available, right? That means that I have a 2 electron deficiency. That means that I have to put one extra bond into my Lewis structure. Okay, so I will remove a pair of electrons from this oxygen and one from the carbon, and I will draw another bond between them instead. Now I have 2, 4, 6, 8, 10, 12 electrons. I have 2, 4, 6, 8 electrons around my oxygen, and I have 8 electrons around my carbon. That's a good structure. Now we'll look at ammonium. We got to do something a little bit different with ammonium because it is an ion. Start the same way. 5 plus we have 4 hydrogens, which is 1. And that gives us 9 valence electrons. Okay, now we have to take into account this positive charge here. Okay, what does a positive charge mean? It means that we are losing an electron. So from this total of 9 valence electrons now, we have to remove 1 electron. Which means that for our structure, we only have 8 electrons available. Okay, so now we're going to write out our skeleton. And look what happens here. After we've single bonded each hydrogen to the nitrogen, we've used 2, 4, 6, 8 electrons, which was all we had. Nitrogen has its octet, and each hydrogen has its duet. Now, because this is an ion, we have to do one more step. We have to bracket off our structure, and we have to add the charge onto the outside of the bracket. Okay, so that's the correct Lewis structure for the ammonium ion. Okay, and I think we have one more. ClO4 minus. Okay, we have 7 valence for chlorine. We have 4 oxygens, each has a valence of 6. Okay, now this one's interesting because now we have a different ion. We're looking at an anion now instead of a cation. So we had 31 valence electrons, right? But what does an anion mean? It means that we're going to add an electron to our compound or our molecule here. So we had 31 present in a neutral, ClO4, but now we're going to add 1 electron because it's a -1 charge. If it was a -3 charge, we would add 3 electrons, but it's only a -1 charge. So we'll just add 1 electron, which means that we have 32 electrons for our structure. Now, out of these two atoms here, which one is more electronegative, chlorine or oxygen? Have to go back to your electronegativity table to figure that out, right? What chlorine is. So it will be our central atom. Chlorine does not like being a central atom, but when it's put into a compound with oxygen, it has to be a central atom because oxygen is more electronegative. I'm going to erase these electrons because I need a little bit of space. Okay, so now I'm going to write my valence back up here. Now I'm going to add electrons, right? My chlorine already has an octet because it has 2, 4, 6, 8 electrons from the bonds. So I'm going to fill the octet of my oxygen and then see where that leaves us. Okay. Now, how many electrons did I use? I used 8 here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, I used 32 electrons. Everything has an octet. The only thing I need to do is to bracket this off because it is an anion. And I'm going to bracket off all of my ions, and I'm going to include my charge on the outside. All right. Let's move back to the lecture. So Lewis theory does what we call localizing electrons. Remember we defined the term delocalized before, so maybe we can make a connection between what that means. It basically has us put electrons into particular places between atoms that are bonding together, okay? But what we know from further study is that there is some degree, I don't want to say complete delocalization, but there is a degree of delocalization of electrons in different Lewis structures, okay? Which means that not all Lewis structures, not all electrons remain as we would draw them, okay? The electrons will move around. Delocalization helps stabilize the charge of our molecule, okay? And we call that concept of delocalization resonance. Okay, that's what we get resonance from. And resonance structures are Lewis structures that appear identical except for the position of particular electrons. Okay, and the actual molecule that we're looking at is more like a combination of the various resonance forms that we could write down. Now, if you're wondering, well, how am I going to know if something's going to form a resonance structure or not? Your key is here. Look for molecules that have multiple bonds in them. Okay, that usually indicates that you have delocalized electrons moving around in your molecule. So we have an example down here. We have ozone, which is O3, and you see that in one form of ozone, we have a double bond between oxygen 1 and oxygen 2. And we can write that same structure basically, except we can put that double bond between oxygen 2 and oxygen 3. Otherwise, there's no different connectivity. It's not like the oxygens are bonded to different atoms of different elements. The only difference between these two structures is the fact that the double bond is here in one structure and it's here in another structure. Okay. And when we talk about the idea of resonance hybrids, we're talking about something, it seems kind of ridiculous, but something like this, right? If you have two purebred dogs and they have a litter, the dog, the second generation is a hybrid of the first two. It's not like it spends half of its time looking this way and half of its time looking this way. It spends 100% of its time looking like a hybrid. And the same is true for our molecules. They don't spend some time with their bond in position 1, 2, and some time with their bond in position 2, 3. Instead, they spend their time like this, where that delocalized electron set that's represented here as dashes, it just moves back and forth between those two positions. That's a resonance hybrid. Okay, so we're going to practice writing out a couple of resonance structures. We're going to write out the nitrate ion and the nitrite ion. And we're going to just look at how we would know that we are actually seeing a resonance form here. Okay, let me switch over to my whiteboard. So let's start with the nitrate ion. we know that that is NO3 minus 1. So we're going to figure out the valence electron number first. Right, so that's 18, 19, 20, 21, 22, 23. Then we have to add our additional electron from the charge, -1 charge. That means that we have 24 electrons total for our structure. Okay, so now I'm going to write out my initial structure. And I'm going to distribute. Let's make everything a little bit more clear. Okay, and we're going to see how many electrons we used up to do this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, that's 2 electrons too many. That means that I have to put a multiple bond in. All right, so I will remove the electron pair from the nitrogen, and I'll remove the electron pair from this oxygen, and instead I'll put a double bond between those two things. Okay, so now everything has an octet, right? 8, 8, 8, 8. And I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons around my structure. So this looks good. So this is one valid structure for the nitrate ion. But it is not the only structure, because I could have just as easily written my double bond between nitrogen and this oxygen, which means that the resonance structure would be this. Okay, everything is the same, except my double bond is on oxygen 2 now instead of on oxygen 1. But why couldn't I have written it between oxygen 3 and nitrogen? Well, I could have, which means that I have one more resonance structure. Okay, my double bond would be between those ones now. 1, 2, 4, 6. Okay, all 3 of these structures are exactly equivalent. All right. What that means is that you could make a resonance hybrid out of them. And let me shorten these brackets up a little bit so I can draw the hybrid underneath. And your resonance hybrid would look something like this. Like you have the little dashes. Okay, and that would be you indicating that you have a delocalized pair of electrons that moves from bond to bond. Okay, that's your resonance hybrid. So let's try the same thing for the nitrite ion. Which is NO2 minus. So now we have 5 plus 2 times 6, 12 and 5 is 17, plus 1 electron is 18 electrons. Okay, so now we'll start by drawing out our skeleton. Okay. How many electrons did we just use up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I have 18. So again, that's a deficit of 2 electrons. So I'm going to need to remove 2 of those lone pair sets and replace it with a multiple bond. Okay, and then just double check everything. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10. Okay, that looks good. Everything has 8. I meet my my octet rule everywhere. But the same thing, there's no reason why the double bond has to be here. It could easily be between nitrogen and this oxygen. So I need to indicate that with a resonance structure. Okay. Doesn't matter where you put the pairs of electrons on around the atoms, like top, bottom, sides, as long as they're in pairs and you know they're somewhere in the vicinity of the correct atom, it's fine. Okay, but those are our resonance structures, and our resonance hybrid would be this. Okay, so that is resonance. Now, when we're looking at different resonance structures, we might run into a situation where we have more than one structure, resonance structure, or just a different, we call them isomers, which we'll talk about more in chapter 10. We're not really going to talk about them too much right now. But sometimes we have to decide what Lewis structure is the better Lewis structure between 2 potential Lewis structures. Because we could draw out 2 Lewis structures and both of them on paper look like they might be valid. Okay, but there is a way that we can go about checking to see which one of them is more energetically favorable, which is always what we're looking to do. Okay, in a Lewis structure, we calculate an atom's formal charge, and that indicates the charge it would have if all of the bonding electrons were shared equally between the bonded atom. When we're looking at formal charges in a neutral molecule, the sum of all the formal charges should be 0. In an ion, the total of all the formal charges would equal the charge on that ion. Okay? And this is our formula for formal charge. And I would recommend writing this down because I don't think that it's written very clearly in your textbook. So just note it down somewhere. When you're trying to evaluate the difference between 2 structures, you should know that the better structures have fewer formal charges. Okay, so a good formal charge would have a lot of formal charges of 0 in it, for example. Better structures would also have formal charges. So if you had to have a formal charge that was not 0, you would prefer that it would be 1 or -1 versus 2 or -2. And better structures would have any negative formal charges on the more electronegative atoms. Okay, you don't want something like oxygen to have a formal charge that is positive if it can be helped, all right? So let's do an example of evaluating 2 different structures together. Okay, here are 2 structures. And I know that I have the solution to this on the next slide, but I think that the process might be good to see. So we're literally going to go atom by atom and compare the formal charges of each component of both of these structures. We're going to start by listing out the number of valence electrons for each one. So the valence electrons for hydrogen is 1. For carbon, the valence is 4. For nitrogen, the valence is 5. Okay. Now we're going to write underneath that let's make a little key down here of what these letters mean. So V, that will be our valence electrons. And then I'll put N, and that will be our non-bonding electrons or our lone pairs. And then B will be our bonding electrons. That should be like more like an O. Okay, so we have no non-bonding electrons for hydrogen. We have no non-bonding electrons for carbon. And we have 2 non-bonding electrons for nitrogen. Right? Now, this last row, what we want are half of the bonding electrons. Okay, but first we'll just take, first we'll get a count of the bonding electrons. So hydrogen has 2 bonding electrons. Carbon has 2, 4, 6, 8 bonding electrons. Nitrogen has 2, 4, 6 bonding electrons. And underneath B, I'm going to write 1/2. Okay, and I'm going to take half of all these values because those are the values that we actually need. So we need 1, 4, and 3. And then I'm going to cross this out. Okay? So now we're going to take our valence number and we're going to subtract these 2 values from our valence. Okay? So 5 minus 2 is 3, minus 3 is 0. So nitrogen has a formal charge of 0. 4 minus 0 minus 4, carbon has a formal charge of 0. 1 minus 0 minus 1, hydrogen also has a formal charge of 0. Okay, now let's do the same process over here. 1, 5, 4 for our valence. We have none there, and 2 there for our non-bonding. We have 2 there, 8 there, 6 there for our bonding, which is 1, 4, and 3. Okay, so 4 minus 2 is 2. 2 minus 3 is -1 for carbon here. 5 minus 0 minus 4 is +1. 1 minus 0 minus 1 is 0. Okay, so if we have to determine which structure is better between this structure and this structure, you see all of these zeros here on the formal charges, that structure is better. All right, that is how we're going to evaluate those. So we're going to do another example now. If you look at the next example in your packet, it says assign formal charges to each atom in the resonance structures of N2O. Which resonance structure is likely to contribute most to the correct structure? Okay, so we've got 2 times 5 plus 6, 16. So let's see what we can do here. We have N. Now I'm going to put my skeleton structure like this because I would want a nitrogen in the center because it's less electronegative than oxygen. I would not want oxygen in the center of this, of my Lewis structure. Okay. Now I'm going to complete the octet and see where I stand numerically. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so I have a difference of 4 electrons here that means I'm going to need to play around with 2 bonds. So one thing that I see that I can do is I can remove an electron pair between each nitrogen and put a bond there. I can also remove an electron between the nitrogen and the oxygen and put a bond there. Right? That's one valid thing. Another thing I can do is I can, let's draw this, draw it out how it was. I can still remove that electron pair, put a bond here. But instead of putting a double bond here, I could remove this other electron pair as well and put a double bond here. Everything still has an octet, and I'm still using the correct number of electrons. Okay, or start back my normal starting point. I can, instead of removing electrons from my nitrogen, I can remove them from my middle nitrogen and my oxygen, put a double bond there, and remove another one from my middle nitrogen and oxygen, put another bond there. Okay, so those are 3 variations of this structure. But now I'm going to check to see which one is correct by using formal charges. Okay. Now I'm going to start to use some shorthand when I write this. So if you're confused about where I'm getting my numbers, refer back to the previous slide so that you're following along. So I'm going to call this nitrogen 1 and nitrogen 2 in each of these, just so I can differentiate between them. Okay, so for nitrogen 1 here, I have 5 minus 4 plus 2. So that's my 5 valence minus 4 bonding electrons plus 4 non-bonding electrons plus 2 bonding electrons, which is the 4 electrons that are in this bond divided by 2. So that equals 5 minus 6, negative 1. And 2 is 5 minus 0 for my non-bonding electrons here, plus 4. So that is positive 1. And my oxygen is 6 minus 2, 4 plus 2. So that's 0. Okay, those are my formal charges for structure 1. Negative 1, positive 1, and 0. Okay. Let's look at my second structure. So for N1, I have 5 valence minus 2 plus 3. So 5 minus 5 is 0. For N2, I have 5 valence minus 0 plus 4, positive 1. Oxygen, 6 valence minus 2, 4, 6 plus 1. It's negative 1. So for this structure, I have a formal charge of 0, positive 1, negative 1. So just based on what we were talking about before, this structure already looks a little bit better. Okay, now let's do our last one. So for N1, we have 5 valence minus 2, 4, 6 plus 1. It's 5 minus 7 is -2. Oh, it started to not look good. Structure 2 is 0 plus 4, +1. Oxygen is 6 minus 2 plus 3, also +1. Yeah, oxygen does not like to be a +1, so that structure is junk. All right, so out of all these three options, this is the biggest contributor here. This meets most of our criteria that we laid out before, okay? And now let's briefly talk about what the exceptions to the octet rule are, because of course there are going to be exceptions to it. And we're going to cover three in particular. The first is when we have an odd number of electrons. These are called free radicals. And those are always going to end up having one unpaired electron in them. They are extremely reactive because nothing likes having an unpaired electron. We're going to look at incomplete octets or shrunken octets. Those are things that do not meet the 8 electron standard that we use, okay? They don't need as many electrons as everything else. Those are things like boron, beryllium, hydrogen. Those have incomplete octets. Expanded octets also. Those are elements that have a lot of empty d orbitals, which allows them to actually hold more than 8 electrons when they are reacting with some different species. Okay, so let's look at these examples here, writing the Lewis structure for the following, and we're going to see different examples. We'll see an example of each of the situations that I just mentioned. Okay. So let's start with NO2. You know that nitrogen has 5, 2 oxygens are going to have 12. So that's 17 valence. Right away, you see this odd number here. You know that that's not going to be great. So we'll write out our skeleton structure. Okay, and we're trying to fill the octets of everything here. So and we would want to do this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, we can't do that, right? Because we have a 3 electron deficit. So we can form a double bond here. And at least now we have 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons here. But we only have 17 electrons present, right? This is our number, 17. So we have to remove one of the electrons from one of the species here. Now, how you're going to decide which one to remove the electron from is you're going to pick the least electronegative atom. So we're going to take that electron away, and we're going to leave this very unsatisfying looking Lewis structure here. That is our Lewis structure for NO2. Extremely reactive, right? That's not going to stay like that for very long. Okay, let's look at BH3 next. Boron is in group 3A, so it has 3 valence electrons. Each hydrogen will have a valence electron, so that's 6 total. Hydrogen has to be terminal, so boron will be in the middle. And what happens after we attach each hydrogen? 2, 4, 6. Well, we ran out of electrons. This is an example where we would have a shrunken octet or an incomplete octet. Okay, and it does happen with some of the smaller atoms. Okay, but nothing we can do about that because we don't have enough electrons to make anything else happen anyway. Okay, now we did mention while we were talking about noble gases earlier that sometimes we can get the bigger ones to react with with some material under extreme circumstances. I'll put that in quotation marks. But we can get them to do it, okay? So when they do, sometimes they do, sometimes these are the examples where you're going to see these noble gases, these, especially the bigger ones, where they're able to expand and hold more electrons in them, okay? So we know that xenon has 8 valence electrons, and each fluorine will have 7. So we have 22 electrons present here. We know that xenon is not electronegative. So that will be our skeleton structure. And now we'll try to feel the octets of everything. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, and everything has an octet. What do I do? Well, xenon has those d orbitals. It can basically make room, and it can hold extra electrons around it. So if you end up in a situation where you have more valence electrons available than you have space for them, put the extra electrons around your central atom, okay? Let's go right into XEF4 from here. Okay, so now we're going to have so now we have 8, 16, 24, 32 electrons around our structure, and everything has an octet, but we have 36 electrons. So we're going to have to actually expand xenon even more this time. And xenon's going to have to hold 2 extra pairs of electrons. Okay, so those are your examples of your exceptions to your octet rule. Okay, and the last thing that we have to talk about for this chapter are bond lengths. Okay, bond lengths and bond energies. Those two things kind of go together. When we say bond energy or bond enthalpy, we're talking about how much energy it's going to take to break a mole of a bond in a particular compound. And this compound would be in its gas state. And when we're talking about breaking the bond, we're saying that each atom would get half of the bonding electrons in the bond that's being broken, or the bonds that are being broken. A bond energy value is always a positive value because breaking bonds is always an endothermic process. All right. Chemical reactions in general involve breaking bonds in your reactant molecules and then creating new bonds in your product end. Okay. So you see down here in this formula, you can calculate the delta H of a reaction by taking the sum of all of the bond energies of the bonds that you break, and this value would be a positive value because it's endothermic, and then adding it to the sum of all of the bonds that you formed, but you're going to make that a negative value because it's an exothermic process. So you're going to take bonds broken and add it to the bonds formed value. Positive value plus a negative value. And that will give you the delta H of the overall reaction. Okay. In general, both of these are generalized statements here. Okay, so you have to keep that in mind. When you are comparing the bonds of similar atoms, you're going to notice that the more atoms where the more electrons that two atoms share, the stronger that covalent bond is. So you see that numerically here, the triple bond is 837 between two carbons. The single bond only has an energy of 347. For carbon and nitrogen, it's 891 versus 305. Okay. Also, in general, the shorter the covalent bond, the stronger it's going to be. Okay, and you can do this by comparing similar types of bonds. All right, so you see if we're taking bromine bonds and we're moving from the top of the periodic table to the bottom of the periodic table, we see that the bonds are getting weaker as we move down the column. Bonds are also going to get stronger as we move across the period. Okay, this is just, I put up the formula again so you can look at it one more time because we're going to look at two problems here. Okay, because we're going to use the bond energies of the different components of a compound to calculate delta H values for the reactions. Okay, and this really works best when all the reactants and all the products are in a gas state. So let's look at, this is just a whole big list of the bond energies that you can reference when you're doing problems. You do not have to memorize this table, you just have to be able to use it. But let's look at two examples. So use bond energies to calculate delta H for the following reaction. And I pulled the bond energies off the table already so we can look at them. Notice that you have to be really specific in the bond that you're looking at. So I'm going to, for CH4, I would actually physically want to visualize what this compound looks like. Okay, I'm going to actually switch to my whiteboard just so you can see how I would look at the reaction before I tried to solve this problem. Okay, so this is what this would look like for me. And I really recommend, in terms of bond energies, that this is how you approach it when you're still getting used to it. So this is my CH4. When I draw it out, I can see that I have 4 carbon-hydrogen bonds here. This is my H2O. Each H2O is going to have 2 OH bonds, which means I have 4 OH bonds total in my H2O. I've got 4 H2 molecules, which means I have 4 HH bonds. And I have 1 CO2 molecule, and when I draw out my CO2 molecule, I notice that I have a carbon with 2 oxygens double bonded to it. So I have 2 CO bonds that are double bonded. And in particular, this bond has a special value. Again, you don't have to memorize it, but you have to recognize the fact that CO2 has double bonds in it to be able to answer the question. So once you have values for all of these, now you can go back and you can set up your actual equation. Okay, now we can actually look at this and say, well, my delta H is going to be the sum of my bonds broken plus the negative sum of my bonds formed. So it's going to be 4 times the 414 for the CH bonds plus 4 times the 464 for the OH bonds plus 4 times negative 436 for the HH bonds plus 2 times negative 799 for the CO bonds. That gives me an overall delta H value of positive 170 kilojoules. Okay. Now I'd recommend you pausing and trying this on your own. I'm going to run through it now. Okay. My delta H is going to be 946 kilojoules from my nitrogen bonds plus 3 times 436 from my hydrogen-hydrogen bond plus 6 times negative 464 for all of my NH bonds in the 2 ammonia molecules that I have. That gives me a total delta H value of negative 530 kilojoules. Right? Again, the bond energy and bond length are kind of connected. When we're talking about bond length, we are looking at the distance between two nuclei of different atoms. We see that triple bonds are going to be shorter than double bonds that are shorter than single bonds. And we see that bond length decreases from left to right. So a carbon-carbon bond, for example, is 154 picometers. And if we move further to the right on the periodic table towards oxygen, a carbon-oxygen bond is 143 picometers. And this is going to have to do with the electron attraction, things like that, okay? Bond length is also going to increase down a column, right? So if we're looking at something like a fluorine-fluorine bond, that's 144 picometers. If we move down the column and we look at a bromine-bromine bond, that's 228 picometers. And some of this is going to have to do with size differences too. Fluorine is much smaller than bromine. So obviously the distance is going to have to increase as these things get larger. And longer bonds are weaker bonds, okay? This is a list of some average bond lengths, but again, you don't have to memorize them. You just have to know how to use them and what their general trends are. And that is the end of chapter 9. I would recommend practicing a lot of Lewis structures. We also need Lewis structures again for the molecular geometry that we're going to do in chapter 10. So it really pays off to get very good at drawing them, get really comfortable at it. Let me know if you have any questions.